A vertical spring with spring constant 70 newtons per meter has a 2 kilogram mass attached to it. The mass oscillates with amplitude 0.15 meters. So we saw in previous videos that this function here will satisfy the equation of motion. So this function will describe the position of the mass at any time t. So here's the position of the mass when it's in equilibrium. It's at x equals 0. Well, it's the position of the top of this point on the spring actually. Let's take upwards as being positive and downwards as being negative. So A is the amplitude. Normally this is taken to be positive, but it could actually be negative. So A in this case is 0.15. What about omega? Well, we know for a spring that omega is the square root of k over m, where k is the spring constant. The spring constant is 70. The mass is 2 kilograms. We have the square root of 70 divided by 2, which is the square root of 35. So we can fill these values in here to get x as a function of t. Now phi can be any value we like. Phi depends on the initial position, that is the value of x at t equals 0. If we plug t equals 0 in here, we get 0.15 sine of phi. So it depends on where we start the timer. So this mass is in motion, oscillating up and down with an amplitude of 0.15 meters. And the position at time 0 is given by 0.15 sine phi. But we could set, say, phi equal to 0, in which case the position at time 0 is 0.15 times the sine of 0. The sine of 0 is 0, so that's 0. So we could have the mass starting here. Of course, it doesn't just start moving if the mass was resting here, but the idea is that it has been in motion already, and when it passes through the equilibrium position, we set the timer to 0, so the timer starts and when x is 0. So that's one possibility. We could just set phi equal to 0, and that would simplify things considerably. And that's actually what I will do. So I will set this to 0. Well, when I say it simplifies things considerably, it doesn't really, the value of phi has no effect on the amplitude or the maximum speed, which is actually this quantity here, or the maximum acceleration, this quantity here. So phi doesn't have any effect on those, and they're the key features of the motion. So now to get the velocity, we just differentiate x with respect to time. And we've seen that before. The derivative of sine is cos. We differentiate omega t with respect to t to get omega. So we get v of t equals a omega cos omega of t. To get the acceleration, we differentiate the velocity with respect to time, and we get back the sine function. The derivative of a cos function is minus sine. When we differentiate omega t, we get omega. So we get omega times a omega. So we have a omega squared here. And then we can fill in the values for a and omega. Omega is root 35, a is 0.15 meters. Here we have a useful applet for simulating simple harmonic motion. So we're going to use the values that we discussed. A spring with a spring constant of 70 newtons per meter, a mass of 2 kilograms, and an amplitude of 0.15 meters. So we can look at this motion and generate graphs. We can bring up the position vector. Just select components. So here we have the position vector. This is x of t. Now we can pause the motion so we can have the timer occurring when the position is 0. T equals 0 when x is 0. That's what we have decided on here. When t is 0, x is 0. The particle is in its equilibrium position. Now let's look at a graph of its position. So we select position here. Move this out of the way. If I just rewind this a second. Now let's set this in motion. We can also show the projection of this, of the top of the position vector. We were looking at the graph of x, which is 0.15 sine root 35t. The amplitude is 0.15. That's this number here. So the range of this function is from minus 0.15 to plus 0.15. We can see that on the applet here. If we freeze this applet, say freeze it here, the amplitude is 0.15. This is 0. Now let's look at the frequency of this function. Well, we could start by looking at the period of this function. The period, as we saw before, is 2 pi divided by omega. Omega is root 35, so we 2 pi divided by root 35, that's approximately 1.06. That's the time taken for one complete oscillation. So mass starts at x equals 0, and in one oscillation the mass will be back at x equals 0. So this time interval here is the period. It is 1.06 seconds. So we're talking about the distance from 0 to this point here. This point here is approximately 1.06. The frequency is 1 over the period. That's 1 divided by 1.06, 0.94 Hertz. This is the number of cycles in 1 second. So if we looked at a time interval of 1 second, it would actually be about here. Say from 0 seconds to this point here is 1 second, because this point is 1.06. So 1 second is quite close to 1.06. So we want to see how many cycles, how many oscillations have occurred in a time interval of 1 second. That is the frequency. And the number of oscillations is 0.94 of an oscillation has occurred. Not even one, not even a full oscillation has occurred in 1 second. Now let's look at the velocity vector. So I'm putting the tail of the velocity vector on the particle. And you can see how the magnitude changes. The velocity vector drops to 0 when the particle reaches its highest or lowest points. The velocity vector has maximum magnitude when the particle passes through x equals 0, the equilibrium position. See, it's maximum. We can also show the velocity vector at the origin. That means its tail is fixed at the origin, x equals 0. So we have two velocity vectors, one at the origin and one at the particle. Both velocity vectors are identical. They're just positioned in different places. Notice that when the position is 0, when x is 0, the speed is a maximum. See, at this time here, the value of x is 0, but the speed is a maximum. And vice versa. When the position or the displacement of the particle from the equilibrium position is a maximum, the speed is 0. So the particle briefly stops when it reaches its maximum height or its minimum height. At the minimum height, the speed is 0. Here again we see it. At this value of t, the speed is 0, but x is a maximum. Here is a rough sketch of the velocity against time. The velocity is 0.15 times root 35 cos root 35t. To 2 decimal places, 0.15 times root 35 is 0.89. So that the amplitude for the velocity is 0.89. So the range of the velocity function is from minus 0.89 to plus 0.89. Notice that when x reaches its maximum, then v is 0. And when x is 0, the speed is a maximum. The speed is 0.89. So this will be the maximum speed. 0.89 meters per second. So a velocity of minus 0.89 is a speed of plus 0.89. You can see here when the position is a minimum, the velocity is 0. And when the position is 0, the velocity is 0.89. If we think in terms of v being the derivative of this, which it is, we can see that the derivative of x at this value of t is the slope of the tangent to the curve at this value of t, and that slope is 0. So v is just dx dt. So whenever tangent has a slope of 0, then the value of v is 0. And at this point here, the slope of the tangent is actually plus 1. Or not plus 1, sorry, but plus 0.89. And at this value here, the slope of the tangent is minus 0.89. Now the amplitude of the velocity looks less than the amplitude of the position on this graph, but that's because the scales are actually different. The amplitude of the velocity is 0.89 as we saw, whereas the amplitude of the position is 0.15. It's just that the scales are different. We can bring up some data here. If we click on data, we can see the position. It's not called x here, actually it's called y. I called it x, we normally call it x, but if we step through this motion, we can see y changing. See, y reaches its minimum value, which is minus 0.15, and then you can see it's increasing again up through 0. You can see y is increasing through 0, reaching its maximum value. So y is this vector here. Its maximum value is 0.15. But look what's happening to the velocity. The velocity drops to 0. The velocity reaches its maximum, or the speed I should say, reaches its minimum or maximum value of 0.89. So now the speed is increasing through 0 and up to 0.89. That's the maximum speed. Then the speed decreases again. The velocity is positive here. Now the velocity is negative. The speed is still positive. The velocity now is minus 0.89 meters per second, but the speed is plus 0.89. That's the maximum speed. Now let's look at the acceleration. Let's show that on the graph. The acceleration is related to the force. It's in the same direction as the force. By Newton's second law, F equals ma. So when the acceleration is high, force is high, and vice versa. Here is a graph of the acceleration. It starts at 0 because the sign of 0 is 0. The range is from minus 5.25 to plus 5.25. It starts decreasing initially and then increasing. If we just look at the sine function, it would look like this. It would start off increasing, but because of the minus sign, it's flipped over. I should have mentioned that the period of all these functions, x of t, v of t, and a of t, is the same. The period is 2 pi over the square root of 35. See, we have the same coefficient of t in each function. Let's start this motion from 0 again. Pause it here. The acceleration is this yellow curve here. Notice that the position, which is the blue curve, is a maximum. When the position is a maximum, the acceleration, the magnitude of the acceleration is also a maximum. See, the maximum value of this blue curve corresponds to the minimum value of this yellow curve. So the magnitude of the acceleration is a maximum here. The acceleration is negative when the position is at a maximum position, a maximum height. We see it here as well. When the position is at its minimum, then the acceleration is a maximum, which means the force is a maximum, because F equals ma. So whenever the mass reaches the extreme ends of its motion, its highest or lowest points, then its acceleration, the magnitude of its acceleration is a maximum, or the magnitude of the force acting on it is a maximum. We also see that when the position is 0, the acceleration is 0. So when the mass passes through its equilibrium position, x equals 0, the force on it is 0, which means the acceleration is 0. You see this here as well. Here I'm just showing the position and acceleration vectors. So when the position vector drops to 0, the acceleration vector is 0. When the position vector reaches its maximum magnitude, the acceleration vector is at its maximum magnitude. So the force will be at the maximum magnitude. So the maximum magnitude for the position is 0.15 meters. So we see it here, 0.15 meters. And the acceleration is now at its maximum, which is 5.11. Well, we got 5.25. Yeah, 5.25 is, yeah, that's what we got before. And if we step back through this again, we can see the position vector dropping to 0. Position vector is 0. The acceleration should be 0 as well, allowing for rounding here. It's practically 0. And as we step through this again, until the position goes to minus 0.15 meters, the acceleration reaches its maximum value of plus 5.25. So the acceleration is in the positive direction. So the force would be got by multiplying 5.25 by the mass. The mass is 2 kilograms. If we want to calculate the force, it's in the same direction as the acceleration. Now we can also bring up a reference circle. Earlier I said that the motion of a particle undergoing simple harmonic motion can be modelled by a point moving uniformly on a circle whose radius is equal to the amplitude of the motion. The amplitude is 0.15. We can show a projection here. So the point is moving with uniformly around the circle. Speed is constant. We can also show the velocity. The magnitude of the velocity of this point moving around the circle is the maximum speed of the mass. step through it here, we see now the magnitude of the velocity of this point is the speed of this point in the circle, and it's equal to the magnitude of the maximum velocity of this mass. This occurs when the mass is passing through its equilibrium position. We can also look at the acceleration of the particle. We can see that the magnitude of the acceleration of this point on the circle is equal to the magnitude of the maximum acceleration of the mass. If we step through this, see when the point is on the lowest point of the circle, we can see that the magnitude of the acceleration of the point is equal to the magnitude of the maximum acceleration of this particle. Acceleration decreases, then reaches a maximum up here as well. For uniform circular motion, the speed of the point is omega times r, where omega is the angular speed of the point and r is the radius of the circle. So in this situation, the projection circle has a radius equal to the amplitude a. That's 0.15, so we 0.15 by root 35, this value here, which is approximately 0.89 meters per second. So that's the maximum speed of the mass that's oscillating. In uniform circular motion, the acceleration of a point is on the circle is omega squared times the radius of the circle. So we set the radius equal to a, and we get the maximum acceleration of the mass, which is this value here. I just take the magnitude of this value.